Well, a good place to start with stars would be, well, where are stars from?
Okay, so stars are the things out there that basically give us light in the universe. So we were familiar with our own sun, the one that basically is responsible for making our planet nice and warm. Every other bright light you can see basically out there at night, apart from the things which are obviously planets in our solar system, are basically stars. There are billions of these in our own galaxy. They all come from pretty much the same sort of way, so that you start with a bunch of dust and gas out there somewhere, which very slowly over time sort of like falls together under its own gravity to reach the point.
What do you mean by falls together under its own gravity?
Well, in the same way that if I jumped up, I wouldn't keep floating off into space. I can get pulled back down to Earth. If you imagine having a whole bunch of little particles out there, like dust grain size, bigger than that, perhaps, they're all pulled towards each other because they all have their own minute little gravity, and they all end up essentially falling into the center, so that they come together. And when enough of them come together, just sort of like straight physics, that material starts to heat up just because of the pressure involved. And eventually it heats up enough that it kicks off a fusion reaction. So you start basically slamming together hydrogen atoms, or rather the nuclei of hydrogen atoms, and turning them into helium, the same sort of thing that we're trying to do in practice down in the south of France with the ITER fusion reactor, basically pushing two hydrogen atoms together. If you can get those to happen, and they turn into helium, it gives off a little bit of energy. And that energy keeps the heating up process going, so eventually the star turns into something which is basically full of radiation emitting out into the universe.
So hang on, could you briefly describe the difference between hydrogen and helium, I suppose? What is hydrogen? Really?
Okay, so hydrogen is the simplest atom we have. Hydrogen is basically, you sit there, it's the lightest atom. All atoms are made up of both the nuclei of the atoms, which is sort of sitting there in the middle, if you can imagine it like that, plus a bunch of electrons sort of orbiting around them. Let's forget about the electrons for the moment, they're not really important to this. So it's the bit in the middle, the nucleus of these atoms. So hydrogen is the simplest thing you can possibly have. It's made of one particle in the middle. It's got one proton sitting there. And helium...
So for instance, in a typical atom like oxygen, which we all breathe, what's in that really?
Oxygen is... I forget how many protons it is. Oxygen has essentially a bunch of protons and neutrons together, so that the neutrons help to shield the protons. It's 16. Yep, 16. So actually oxygen is quite straightforward on it. So oxygen has 16 protons and neutrons, and there's actually equal numbers of each. They essentially just sit there. The neutrons are a useful thing in the sense of, normally when you have just all these little protons are positively charged particles, so if you push them together they try and repel each other, whereas the neutrons, as their name suggests, are neutral, and they help shield the protons from each other, so they sort of travel around in pairs a bit. So when you try and push two hydrogens together, obviously that's just made a proton in each one. There's that force there trying to push them apart, so you need to get really lots of force going in the other direction to push them over the other edge, and that's where essentially you keep building up the mass in this early stage of a star until the gravity forces these atoms together. Then helium is the next simplest atom. It's actually just two protons and two neutrons. So when you shove the two protons together, they can basically turn into the core of what's going to become a helium atom. They turn into something which is essentially going to be bigger than that, and they sort of sweep up some of the neutrons around them and form this helium nucleus as well, and give off energy. And that's how our sun works, essentially. It's just
so the kind of joining of these two atoms is what creates the energy, is
absolutely, yeah.
Okay, so well, you've explained kind of where stars are from, but are the first stars different to kind of where our sun came from?
Yeah, so I mentioned something about stars forming from dust and gas out there in the galaxy. So there are all these clouds of things you can actually see at night. If you sort of have a very clear night, you can see sort of like dusty lanes in the Milky Way. If you imagine going back to the very early universe, it's actually very different. So all that dust and gas has actually come from other stars. So stars from the end of their lives, as we'll talk about in a minute, basically chuck out material as well. And you can't form that kind of sort of like obscuring dust and gas until you've had stars formed already. So it almost sounds like a catch-22 situation here. So what happens?
So you need basically old stars to form new stars.
Pretty much,
but
yeah.
The question is, where does the first star come
Yeah.
from? Okay.
So the first stars instead form out of what's just the material around them in the universe. And in the early stage of the universe, there's nothing apart from hydrogen and helium pretty much. So that's all you've got. You've only got those two elements. The stars basically, they will try and come together. They still try and pool together. But it's very hard to do because the material they're made out of is not very sort of stable for forming stars on its own. It's much easier to form stars once you've got heavier elements around. So it just takes a lot longer. And the other big difference is that rather than forming stars like our sun, we think the first generation of stars, because they're only formed of these very light hydrogen and helium elements, actually grow up to having masses which are more like 100, 200 times the mass of our sun. So it's enormous monsters.
What time frame would you say these stars were formed? I mean, how old is the universe is the first question. And when were the first stars formed, and when were these stars formed?
The universe is about 13 billion years old. The first stars formed, roughly speaking, after about 1 billion years.
That's quite a while before four stars start to form.
Partly it's just you need to get the universe, as it evolves, gets cooler with time. It's getting sort of larger, and that essentially means that the energy gets spread out more, so it gets colder in any average place. And you need to get the temperature down before you can actually make the stars form. Otherwise,
so the star needs to be cold before it can.
Well, the materials
hot.
The materials being made from needs to be cold. Otherwise, just the pressure of the from the motion of the particles in this sort of like nice warm bath essentially keeps it going, so it keeps it from collapsing into the star.
So when you've got a star, how does it really give us heat? How does it produce energy continuously? Because it doesn't seem to stop. Every day the sun seems to keep on working, so how come it keeps on working forever, really?
So once it's swept up all this material into this ball, and it's sitting there, once it started fusing these hydrogen nuclei into helium nuclei in the center, that's a continuous process, because essentially the energy that comes out of that helps to kick off other reactions that are going on around it. In particular, you get sort of like a chain reaction going through the center, and eventually you end up at a state where the core of the star itself essentially has this little nuclear reactor in it, effectively. That radiation from that nuclear reactor permeates outwards through the star very, very, very slowly, so that the radiation from the center of the sun, for example, takes hundreds of thousands of years to actually get its way to the surface, because the process of transferring
the energy
is slow.
stuck in the sun. It's basically stuck. It can't get out.
It's not stuck. It just takes a long time to come. So it's like a steady, continuous process. It's always happening. But the energy, which basically we see radiating out to us now, started its life as a reaction in the core of the sun a long, long time ago, well before sort of like Homo sapiens were meandering around in terms of sort of doing.
So that's
things.
humans.
Yeah. So that the process is quite slow in that sense. It only stops when you run out of fuel. So as long as you've got hydrogen there, you can keep this reaction going. Eventually, however, since it's nothing sort of perpetual motion machine, you run out of hydrogen.
So when will that happen for our sun, for instance?
So our sun, roughly speaking, is 5 billion years old, and it's got about another 5 billion years worth of fuel.
So we've got a while to
We've
worry.
got a while, yeah. And at that stage, that star essentially has a problem, because you've basically used up all the energy that you had in the middle. You have to basically try and do something to keep the star holding itself up. So this comes back to the idea of why doesn't our sun turn to supernovae? And what happens once you've used up all the energy in the middle is you start using it, basically fusing all these hydrogen atoms around the middle instead. So you form a little shell around the middle bit, which then starts to have the sort of like hydrogen fusing to become helium. But because it's no longer in the middle, it changes the whole configuration of the way the star works. So at that point, the star itself tries to swell up and becomes what's called a red giant. So one of the other things that will happen in 5 billion years' time is that the sun, rather than being this very distant thing, will actually swell up. We now believe it will pretty much not swallow the Earth, but it will be so close that essentially, if you looked up into the sky, rather than seeing a sort of small disk being the sun, the entire sky when it was up would be the sun. You basically wouldn't be able to miss it.
So you're saying when the sun runs out of fuel and starts to die, it actually gets warmer and tries to eat the Earth?
It doesn't get warmer, it actually gets cooler as it swells up.
Bigger.
It gets a lot bigger though, yeah.
Okay.
And it's one of the ways it compensates for the fact it hasn't quite got enough energy to keep going, holding itself up at the centre.
So we're pretty sure it's not going to engulf the Earth, but it will be too hot to live on the Earth.
I think we believe at the moment that it's probably not quite going to swallow the Earth. There again, we believe 20 years ago it probably was just going to swallow the Earth. So these things are quite sort of finely balanced. We're not absolutely sure. But because it's so close to the Earth now, because that surface of the Sun is basically, rather than being 150 million kilometres away, it's perhaps only a few million kilometres away. Essentially, even though it's much cooler, it's so much closer that, yes, it'll bake the Earth.
Right, so I don't want to be living on the Earth in 5 billion years. Okay. So what happens to the Sun after the red giant stage, or any star, really?
Okay, so the Sun will carry on from then. Essentially, it continues this process of trying to fuse together hydrogen and helium in different parts of its interior, but eventually it runs out of places it can do that, because essentially the thing that's basically causing that to happen in the first place, the gravity that's pushing it inwards, it just can't do it for far enough out in the Sun's atmosphere that where there's still the hydrogen left. So you just run out of fuel, and at that point the star will start to shrink. So the Sun starts to basically get smaller again. Eventually it will stop getting too small because it's held up by other pressure, things that are probably beyond what we want to try and explain here. Essentially there's that other sort of like forces that can try and hold something up when it gets at that stage of the star's life. But it's run out of fuel, so it will no longer radiate apart from the radiation that's still trapped in there, trying to leak out very slowly.
So it no longer produces light, basically. It just uses the light it's already got. Essentially,
yes. So it turns into what's called a white dwarf, having been a red giant. And this white dwarf, over time, actually just fades slowly with time, and actually gets redder again with time as well. So it goes from being white. The reason it's gone white again is because it's got smaller. Because it's got smaller, the energy is there, can make the surface a bit hotter again for a while. But then, as it basically has no replenishment of the sort of like energy coming into this thing, it just fades away slowly with time. So the oldest of these white dwarfs are actually bizarrely red in colour, but they're still called white dwarfs.
So, do all stars die the same way?
No.
So what's different to our Sun and
okay, so
other stars?
There's three different ways in which stars die. There's basically stars like our Sun, of the same sort of mass as our Sun. They all do the same thing. Stars that are 2 to 3 times the mass of our Sun, they actually get to a much more compressed stage at the end, so that the thing that pressure that's holding them up is a slightly different thing, and they form what are called neutron stars. And these neutron stars are peculiar objects where essentially the whole of the Sun, in that case, the whole of the star in that case, has become a sea of neutrons. There's nothing else. All the electrons and protons have fused themselves together to form neutrons. So imagine a star just made of neutral particles of one kind, and that's what a neutron star is.
It's a boring star.
It's a boring star apart from the fact that they can have really strong magnetic fields for reasons we don't fully understand yet how this is generated. So that's the next step up. And then stars that are bigger still, stars that are 10 times the size of the Sun. Essentially there's nothing that can stop the star from collapsing once it runs out of fuel. And it collapses inwards and then goes bang. It turns into a big supernovae. And that bang is actually important because that's what throws out all the material the star was made from. So when we're coming to talk about how future generations of stars form, planets and things like that, all the heavy elements, things like iron, for example, they come from the centre of these stars that are going bang, because that's the only place that's producing it and turning it back into the universe at large.
Right. So everything we're made of, basically all the heavy stuff, comes from a black hole. Come from a supernova. Pretty much,
yeah. So the lighter elements, the things that are most common in our bodies, like carbon, for example, they can come from stars like the Sun. They throw off material as they go. I'm sure everyone's sort of familiar with the idea of the solar wind, sort of like disrupting communications and giving us the northern lights every so often. That happens throughout a star's life, so it's throwing off stuff, but it's throwing off the lighter stuff typically. It's only the big heavy stuff comes from the cores of these big stars as they collapse and turn to supernovae before they become black holes.
So yeah, very briefly, if you could tell us what are black holes and what are they made of, if that's possible to answer.
So black holes essentially are just these things that I talked about earlier on, where effectively light cannot escape. Light can't basically beat the gravity there, so that the gravity is so strong it holds on to the light as well. And that just means that we can't see inside them at all. 'Cause things can travel into them, but nothing can come back out of them. As to what they're made of, we don't really know, because we don't know what's inside there. Essentially, they should just be mostly space like it is around us. If you could travel into a black hole, if you imagine sort of like crossing through the point of no return, as it were, the point beyond which light cannot escape from, it would look to you as if you hadn't crossed anything. If you look backwards, looking outwards, you would still see the same universe around you. Looking inwards now, though...
That is provided you can make it into a black hole in one piece.
Yes, indeed. We'll come to that in a sec. But looking inwards, what you'll actually see, essentially, is something which none of us can see, because you're now within that event horizon. You can see the thing in the middle. So perhaps then, if someone's daring enough to do this, they can work out what's there. Unfortunately, they can't come back and tell us what it is.